Hi everybody, I'm recording a video on dummy coding, effect coding and contrast because I feel like this is something that is very confusing to a lot of students, but also in general. Like the textbooks I know that had it wrong, some of them at least, in how to use contrasts or what contrasts are. So I want to clarify this a bit in this video because it is a very confusing thing. So let's say we have a very simple design. Let's say we measure some outcome variable like y, maybe happiness or sadness or concentration, whatever. And we have some predictor x. And let's say x is categorical with three groups. We have hamsters, we have cats, and we have dogs. Right, so we have three different types of subjects. Right, a categorical predictor. Right, our data might look something like this. We have y. Let's say we measure 5, 4, and a 6. Right, so the first person responds with a 5, second with a 4, third with a 6. Let's say we have 3, 2, 1, and 8, 7, 9. Now I'm just coming up with this data on the spot. Right, it's just arbitrary. All right, so that's our y variable. Now let's also say we have an x variable. And the x in this case is categorical. Right? So we have hamsters. Let's say the first three subjects are hamsters. The second three subjects are cats. And the third three subjects are dogs. All right. Now we could see, for example, that the average here, well, h bar equals 5. The average here, let's call that c bar equals 2. And the average here, let's call that d bar equals 8. Right, it's just taking the average. There's one below and one above 5, so that's 5. There's one below and above 2, that's 2. One below and one above 8, that's 8. Now, if you want to use this predictor in a regression model, we can't, of course, use a categorical variable like this because it doesn't have numbers. So what can we do? We can form a model where we use dummy variables. So for example, my model can be y, let's say y hat, the predicted value, equals b0 hat, the predicted value for the intercept, plus b1 hat times the first dummy variable plus b2 hat times second dummy variable. A dummy variable, in this case, is just a new variable that we make that is a number that we encode in some way, such that if you're in one group, you always get the same value on the dummy variable. Every hamster will get the same dummy variable for value 1 and the same value on dummy variable 2. Which values are those? For that, we specify something that we call dummy encoding. Let's write it in, I'll write it in blue still. Dummy encoding. All right, so we have two dummy variables, d1 and d2, and we can specify for each of them what the level is for the different subjects we have. We have hamsters, we have cats, we have dogs. Right, so let's say we specify it like this. And actually, interestingly enough, this is not something you actually need to do when you do an ANOVA design because software will do it for you. But let's say we specified it this. So that means that you can, right, again, software will do this for you, but you can think about it like this. We add two more variables. That is 0 on both for hamsters. For cats, the first one is 1. For the second one is 0. And for dogs, the second one is 1, and the first one is 0. That's what we call the dummy encoding. Now, we know that the predicted value should be the average in each group. That is because the errors should sum up to 0. So we know that if we fill in this formula for each group, right, we get the same effect, right? So B0 is not different per subject. B1 is, the dummy 1 and dummy 2 are the same, right, for each group, for all subjects in each group. So we get the same value, the same predicted value for each member in a group, and that should average the group means. So that means we can now derive that, let's say, the mean of hamsters equals, and I'll just drop these little heads here to make the notification, the notation a bit more simple. Okay. B0 plus B1 times the first dummy variable, that's always 0, right? So that's nothing, right? So plus B1 times D1, but that's nothing, plus B2 times D2, but that's also always 0. So let's make it a bit nicer. We just remove that. It's just B1. What about the average for, so we know that this is actually 5, right? Because we know the average, we can just calculate that by hand. So we don't actually need to run ordinary least squares regression here. We could actually just derive this by hand. We don't need to know that, but some formulas for ANOVA are designed for that. And actually this is just a one-way ANOVA design. What about cats? Cats here equals B0 plus B1, because, right, this first dummy variable is 1 for cats, plus nothing, because second first dummy variable is nothing, equals 2. Right? And for dogs, we get B0 plus B2 equals, in this case, 8. Because those are the averages that we get. Now, an interesting thing here is that we have 3 unknowns, right? These B's, 3 knowns, which means that we can actually solve this equation and flip this thing around. We could define what these B's look like. So let's do that. We have B0, right? So let's say we can translate this to each other. Let's make it nicer. B0 equals the mean, right, of hamsters, which in this case equals 5. B1. So what is B1 here? Well, what we could look at is, for example, what happens if we do the mean of cats minus the mean of hamsters, right? And then we get B0 plus B1 minus B0. These things cancel out and we're left with B1. So that means that the B1 parameter is actually the average of cats minus the average of hamsters, which in this case equals 2 minus 5 equals minus 3. Now I can do the same thing for B2, right? So that's the difference between dogs and hamsters, right? If we derive it in the same way. Let me actually remove this here to make sure it's cleaner. If we derive it in the same way, we would get 8 minus 5 equals 3, right? If you enter this data in JASP and you run this multiple regression model, you should get these parameter estimates. Now this is a one-way ANOVA design, right? We can see that if these B1 and B2 are both 0, there's no difference between the groups. They're all equal. And that's what the one-way ANOVA will do for you. Now this is actually not that important that you can do this by hand. I just wanted to show this. What's important is this part here. So what does this regression model allow us to do? It allows us to do an f-test to see if these are both significant, see if they're both non-zero. What happens if B0 or B1 is 0? There's no difference between hamsters and cats. They're the same. What happens if B2 is 0? There's no difference between hamsters and dogs. If hamsters and cats are the same, the average at least, and the average of hamsters and dogs are the same, then by extension, the average of cats and dogs are also the same. So if we test with an f-test, if both these parameters are 0, which is what a one-way ANOVA does, we test if there's any difference between the groups. Now we get some more interesting thing. These parameters also have associated t statistics that we can use to test hypotheses on the parameters themselves. For example, we might have an hypothesis, let's say, that the average of cats is higher than the average of hamsters, right? And that's associated with a null hypothesis that the average of cats equals the average of hamsters. That is the same as saying that cats minus hamsters equals 0, which is the same as saying, in this case, beta 1 equals 0. So that means that these parameters encode what we call effects. So these three are effects. Now, let's write this down a bit more elaborate. If B0 equals, we could also write it down like this. B0 is, well, let's forget about B0 actually. It's not that interesting, right? Because that's just the average of one group. That's not 0. We're interested in these B1 and B2, which tells us something about the effects of the groups. Right. Let's say B1 equals 0, minus 1 times the average of hamsters, plus 1 times the average of cats, plus 0 times the average of dogs. Okay. Minus 1 times the average of hamsters, plus 1 times the average of cats. That is equal to saying the average of cats minus the average of hamsters, and this thing actually does nothing. B2 equals minus 1 times the average of hamsters, plus 0 times the average of cats, plus 1 times the average of dogs. It's just writing this equation in a slightly different way, but it's the exact same thing. Now you see here that we have two effects here that we're interested in. This intercept is basically always there, right? So there are two effects here that we get associated t values for. Now, this means that every regression parameter in my regression model, if I have these dummy variables, is encoding some effect, right? Something that I might be interested in. Now the thing is, it's quite hard to see that, right, from these zeros and ones, what the effect is. Right, we have to derive that in this case. And you might be interested in these effects, or you probably are interested in these effects, and not necessarily in these dummy variables. The nice thing what we can do is we don't actually need to specify the dummy variables. What we could do is we could do something called effect coding or encoding. What we are then doing is we are not specifying this, how do you encode the dummy variables, but we're specifying this. We're specifying how should the dummy variables be encoded such that we get the effect of interest. So that's, I want to make sure that B1 indicates the effect of interest and B2 indicates some other effect that I'm interested in. And I'm not actually interested in the exact encoding for the dummy variables. right? This is what we also call contrast. Our first contrast or second contrast, those are the effects that we're interested in. We can specify. And in this case, we have here a -1 for hamsters. And that leads to a -1 here. Same for the second contrast, this one and this one. Then what we see here is we have a +1 for cats. So that leads to a 1 here, right? We have a +0 for dogs. So that leads to a 0 here. And we have in the second beta or b value -1, 0, and 1. So we have -1, 0, and 1, right? And a 0 here. Right, I actually realize now that I should have drawn the 0 earlier here, and this is the 0 I should have drawn now. All right. These are what we call effects and the contrast. So how is this different? So we have here, we have the dummy encoding, and we have the effect encoding. They are different, very different. So the effect encoding is not telling me how the dummy variables are encoded. You see, I did not actually change the dummy variables here, right? They're the same. They're 0 for hamsters. For cats, the first one is 1, and for dogs, the second one is 1. Right? But those dummy variables are encoding these effects. Now, the nice thing is that I can specify these effects and tell Jasp, okay, I'm interested in these effects. I don't care how you specify the dummy variables, just make sure that I get these effects of interest. So I get the t values of interest. And that's actually what's happening here. Right? So it's not the case that if you use effect coding, that these dummies are actually different. The dummies are the same. Now, a very interesting thing here is that after I estimate my model or estimate my parameters, I might be interested in a different effect than I had that I encoded in the original dummy variables. So let's say, for example, I'm interested in the hypothesis that the mean of dogs is higher than the mean of cats, right? Which also translates to the hypothesis that the mean of dogs minus the mean of cats is larger than 0. That means that there's an associated null hypothesis, which says the mean of dogs minus the mean of cats equals 0. Now, this is not an effect that I had in my original dummy encoding, right? Because I have only the difference between hamsters and cats and the difference between hamsters and dogs, right? Not the difference between dogs and cats. But the thing is, I do actually have this information. Let's see what happens if I write the difference between the mean of dogs and the mean of cats. What do I get? Well, I get the mean of dogs, which is B0 plus B2, right? Minus the mean of cats, which is B0 plus B1, right? So then this B0 drops out, and we're left with B2 minus B1. So we see now that B2 minus B1 is actually encoding the effect of interest, namely dogs minus cats. And that means we don't need to go back and change the dummy encoding to get this value, because actually with the associated estimates of standard errors and the covariance, which is not very important, but what it turns out is that you can transform the results you have, you can transform this beast that we have into the effect that we're interested in. Now that's very, very interesting, right? Because we did not have to go back. I did not need to change my bees, right? I can find this effect that I'm interested in. The only problem is that, well, we only had two effects, right? A B1 and a B2. We don't care about B0. It's just an intercept. Those are two p-values. We suddenly can't get like a third or fourth or fifth p-value out of there. But the thing is, it doesn't actually matter at all what the dummy encoding is. Dummy encoding hardly matters. Hardly, because it's actually a very small detail that I'll come back to in a bit. It hardly matters. I can actually just really specify anything here. That's why when you run a one-way ANOVA, two-way ANOVA, JASP does not give you the dummy encoding. It does not tell you, yeah, I actually ran a regression model with these dummy variables. It does not give you the p-values or the t-values of these b's. It doesn't give you the b's because yeah, those are quite hard to interpret, right? If JASP tells you, yeah, encoded is 0, 1 and 0, 0, 1 and 0, 1, 0, figure out what it means. It's hard, right? And we don't need that because we can use effect coding or contrast to specify the actual effect that we want, and we can get that afterwards by just transforming these b's and transforming these p-values, and JASP will do that for you. That's what we do with contrast. Contrast. What contrasts allow you to do is to specify afterwards what effect you were interested in, and you get the associated p-value for that. And you can do that actually as many times if you want, but the recommendation is to not do it more than you have dummy variables, because yeah, we only actually have two p-values in there, or two significance values, two standard errors. So you are reusing that information if you are trying to get like 3 or 4 or 5 hypothesis tests out of there. That's why in post hoc tests, where we do compare all groups together, we have to adjust for multiple testing. But when you use a contrast, it is usually an effect that you thought of before, like a certain hypothesis that you thought of beforehand. You don't have to adjust for multiple testing because you are not doing too many, or you should not be doing too many. So it's a weird thing. And they look very similar, right? Dummy encoding and effect coding, like you write it down almost similarly. But they're very different, right? These are clearly two different things. They're encoding the same effect, right? So I did not change anything. These dummies here are encoding these effects. That means we could actually, if we run a regression model, specify exactly how we encode the dummies, or specify which effects we want. And usually, yeah, this is what you do. Or actually, this is what you can do afterwards, because you can just get this information after. So you don't need to specify dummy variables. You don't need to do that at all when you use good software like JASP. When you use R, it's yeah, you also just get a default dummy encoding, and then afterwards you can just get the effect that you're interested in. So does that mean that dummy encoding completely doesn't matter? Well, not exactly. So, but I'll talk about that on a fresh new page. All right, here I cleaned up the page a bit, and I'm going to show you what JASP actually does behind the hood when you do one-way ANOVA. So I always try to explain dummy variables with 0, 1, 0, and 0, 0, 1. If you use R, those are the default dummy variables, which are confusedly called contrast in R, which is just extremely confusing thing. In JASP, and when you run ANOVA, typically the dummy variables are actually encoded in a way that they sum to 0. So for example, I could encode -1, 2, 1, and -1, -1, 2. In the lecture, I use -0.5 and 1, but this is basically the same. Right, so what does it mean? -1, -1, -1, 2, 2, 2, -1, -1, -1, -1, -1, -1, -1, -1, -1, 2, 2, 2. Now the reason why this is done is because if you do a two-way or three-way or four-way ANOVA, The significance of the main effect is based on type 3 sums of squares, is based on the idea where you do this model with and without that main effect. And you still have an interaction effect there. And that interaction effect, if you don't have these dummy variables sum to 0, include a bit of the main effect. And that's why you need to sum them to 0. This is, but you don't actually need to do that. That's just what the software does under the hood. So if ever you want to reproduce a two-way ANOVA as a multiple regression model, you'll see that the f-tests won't be accurate unless you do this. So what's happening here? What is the average of happiness now? Well, we can see we have this B0 still, right? Then plus B1 times minus 1, so minus B1 plus B2 times minus 1, so minus B2. Right? For cats, we have B0 plus 2 times B1 minus B2. And for dogs, we have B0 plus, oh no, sorry, minus, right? So this is minus 1, so minus 1 times B1, so minus B1, plus 2 times B2. It's a bit more complicated, right? But let's say we are interested in the effect, the difference between cats and hamsters, right? So let's say I expect that cats are happier than hamsters, but if not, then the null hypothesis would be that this is 0. So what is this? All right, let's try to do that. We have first B0 minus B1 minus B2 for the hamsters, right? And let's say here for the cats, I should have drawn it better, but okay. B0 plus 2 times B1 minus B2, and we subtract this, right? So this minus that. So what do we get? Well, it's the same thing, right? It drops out. Same thing, drops out. So we have 2 times B1 minus B1 equals B1. So that means that the effect encoding here, the first contrast here, is the same. The same as we had before, right? It's minus 1, 1, 0. The difference between cats and dogs, or cats minus dogs. And the second contrast you will see is also the same what we had before. So that's very interesting because it shows that this dummy encoding actually doesn't matter, right? If it's 0, 1 or minus 1, 2, right? If we define it in a way that it sums to 0, we can find the same effect. Right? That's another reason why it's nice to sum to 0, because otherwise there are many different ways to encode these dummies. Now, what does JASP do? JASP just does this. It will define dummy variables like this. I think it's actually a half, 1, a half, minus a half, 1, minus a half in this case, but it doesn't matter that much. Oh, this should be minus 1, sorry. It just does this, and then it gets b values, which it doesn't report. It gets significance for the b values, which it doesn't report, because you can use the effect coding to change that, right? I can now define a different effect to shuffle these b's around and get the effect that I'm interested in. And that's actually what's happening. The only reason why what we call centering of the dummy variables is important is because if you have a two-way or three-way or four-way interaction of ANOVA design with interaction effects, the significance of the main effects would be a bit different if you don't do that. That's really the only reason why that matters. So it's completely not important, really. It's like a very non-important detail that dummy variables are centered. That's really only important if you ever wake up and you want to specify a multiple regression model. You want to make these columns in JASP yourself and then see that you get the exact same f-test from a multiple regression model than an ANOVA. Right? That's only happens if you have this dummy variables encoded summed to 0. Right, so that's again a confusing thing because these also sum up to 0, these contrasts, right? But, so these are the effects again. And I can specify different effects and then transform these values into the different effects. Right, but there are something different. Right, so the centering of the dummy variables is not the same as the contrast. And this is a very confusing point. Right, so that's why I wanted to make this video. Now the takeaway point here is that if I have, let's say, 3 levels, that means 2 dummy variables. If I have 4 levels, it means 3 dummy variables. Right, it means you can think of a design with a categorical variable, like an ANOVA, as a regression design where you have 1 fewer dummy variables than the number of levels that you have. Now, how that works under the hood, some dummy encoding is happening, right? And that gives you a regression model. It doesn't actually matter what the dummy encoding is, right? If you really want to get technical, those dummy encoding, the encoding of the dummies sums to 0 over the categories, but that's really not that important. What does it give you? A regression model where you can get a joint significance of 2 B's, which will tell you something if there's a group a difference at all between the groups, right, with an F-test, and t-values for each B parameter. Now the nice thing is we can use contrast to transform these parameters and the t-test in the stuff that we're interested in. So that's what JASP is doing. It allows you then after say, okay, I actually want to have a contrast for this group difference. And then JASP tells you, well, okay, that's actually B2 minus B1, and that is actually also significant or not. Right, and that's really the only takeaway message here. Alright, that's it for this video.